Okay, kids, electromagnetic spectrum. Electromagnetic spectrum is really talking about all the kinds of light that there are, even the kinds you can't see. As a human, you can only see a little bit of this spectrum. There are many other kinds of photons, of light particles, that you can't see. In fact, there's way more that you can't see than you can see. There's all kinds of things going on, like radio and your cell phone. They're sending out essentially what is invisible light. Also, the microwave oven works on microwaves. It's sending microwaves into the food, which is just fine. It heats up the water, and that's all it does. It doesn't make it damaged. It doesn't make it harmful. There are many different kinds of electromagnetic waves, and you can find a list of them on that picture, that colorful picture that I attached to this assignment. So, the spectrum just means all the kinds. So, let's talk about a few things. Energy is measured in joules. There is a Mr. Joule, sometimes just capital J. Frequency means here the waves per second. So, frequent means how often, and the frequency is measured in waves per second. And I know somebody just shouted in their brain, it doesn't say waves. You're right, we know it's waves per second, but we don't write waves physically, don't actually write the word waves, or it doesn't make sense in the math and the units don't work, so we're just going to call it per second. Wavelength is literally a wavelength, except sometimes we end up dealing with wavelengths that are very, very short, almost just impossibly short it seems, stuff that is way off the scale of human existence and interaction. But it's measured in meters, even if it's very short. We still measure it in meters. Another way to say the frequency is measured in hertz. Now here's the unit, but also sometimes this is just called Hz for Heinrich Hertz. There was a Dr. Hertz. And so you can use either one, but when we say hertz, we mean per second. And again, it's waves per second, but we just don't write waves. Here's one of our fundamental equations for this, that the speed of light is equal to the wavelength. This is a Greek letter called lambda. That is not supposed to be a letter that you commonly used. So if you're trying to make that into backwards H or something, it is not. It's a letter called lambda. Times the frequency, and we use a Greek letter called nu. That is not V. It's more like a V with a left tail. I realize that's confusing, but just in case you end up in a college science class, you don't call it V. You can act like the kid who knows everything, and you can call it nu, but it means frequency, and it's measured in per second. Our other big formula here is energy equals Planck's constant. There was a pretty famous Dr. Planck. He was German, which is why it sounds a little bit funny. And we need to have that in our equation, and here's the value. We don't have to memorize it. Notice the negative sign there on the 10 exponent, by the way. Times the frequency, again, its frequency is nu, measured in per second. Here's the speed of light. It's always the same. We don't have to memorize it. There it is. Here's Planck's constant. We don't have to memorize it. There it is. For number 1, which is not a math problem, but it talks about electrons falling from a higher level to a lower level. And we talked a little bit about that there are energy levels. We talked a lot about how there are valence electrons. There are outer electrons. Well, if there are outer ones, there must be inner ones. And so we just number them. This is just the rough figures. If you end up in AP class or a college class, believe me, there's a lot more to this. It gets a lot more complicated because sometimes nature is complicated just because it is. But for rough terms, we can just call them level 1, 2, 3, 4, going out from the middle. So level 1, 2, 3, 4, going bigger and bigger from the center, from the nucleus. So, when an electron falls from a higher level to a lower level, how is the energy released? Okay, so if it falls from level 4 to level 2, it gets less energetic. Energy can't be destroyed, so the energy doesn't disappear, it gets sent away. Well, how does it get sent away? Well, the electron invents a photon, a light particle, to send away. It gets to just invent it out of nothing. The energy becomes the photon is the energy, There's no special storage of the photons it has to keep. It just invents a photon and sends it away. Notice I had to correct this a little bit. It releases a photon, which is a light particle, with energy equal to the difference between the energy levels. So just for dumb numbers that aren't true, if level 4 to level 2 has an energy difference of 5 millionths of a joule, because the answer is going to be really small here. Let's say that they're 5 millionths of a joule apart. Well, the electron falls from 4 to 2. It has to remove 5 millionths of a joule from itself. And so it sends away a photon that has 5 millionths of a joule. The energy of the photon is equal to the difference between the energy levels. Number 2, if you go look at that attachment I put on there with the electromagnetic spectrum, and you find the frequency, remember that smaller numbers are more negative. More negative means smaller or bigger is less negative. Give that a moment and give it a thought, and if you go from the low frequency to the big frequency, the number of waves per second, it goes from radio over to gamma. Now, what has more energy? Slow bounces or fast bounces? Slow bounces or fast bounces? I think you can see that fast bounces are more energetic, so a high frequency has more energy. So a high frequency has more energy, a low frequency has less energy. So if we're going on an increasing rate, the energy follows the same pattern. It will be lower energy to high energy. So this is the same stuff in the same order for the energy. Lowest to highest. Three, what about the nature of light can only be explained by the particle model? This takes a little bit of a story. So, here's my metal plate, and I shine a UV light on it. Turns out that when they did this with the right kind of metals and the right kind of light, they got electricity flowing around. The electrons got kicked off, some of them got kicked off the atoms. They started skittering around on the surface of the metal, and sometimes they even just jumped out into the air. Well, that was pretty interesting. So, of course, people had to play around with it. And by this time, they knew that light was a wave because you could see it interfering with itself and so forth. And I asked you to go watch some videos on that. And everybody agreed it's a wave. Yep, we cracked the problem. It's a wave. Got it. Here's the problem. Now, as a thought experiment, let's take our UV light. Let's turn up the dimmer switch. And let's shine more UV light on there. Well, basically what they said was, well, I know what's going to happen. I've turned up the dimmer switch. And there's more UV light. And there's more energy, and so all these electrons are going to get more and more energetic. Except that's not what they got. What they got was more electrons with the same energy as last time. And that did not seem to make sense if light is a wave. Well, this stumped everybody for a while, and in fact, this is the topic that won Einstein his Nobel Prize. I know he's much more famous for some other stuff, but this is actually what the main citation was on his Nobel Prize. He said, I understand that it's a wave, and everybody agrees it's a wave, and I get it. However, what you guys have just described is something else, and here I'm just going to make up my own little analogy. He did not actually talk about marbles, but you got a bunch of marbles, and you start shooting marbles in. If you shoot in 5 marbles, you knock 5 marbles out. If you shoot in 10 marbles, you knock 10 marbles out, that kind of thing. What you guys have just described is a lot more like shooting marbles in than shining waves in. And I understand that light is a wave, but what if it's also, in some sense, a particle? What if it's a wave that's also a packet? It's a packet of a wave, which I know sounds weird, and to tell you the truth, guys, I wish I understood it a little bit better, but that's as good as I've got for you. It's a wavicle. It's a packet of a wave. It is a wave, but it only comes in certain packets. And that appears to be the correct answer. Everybody pretty much agrees that that is the way it works. Sometimes it acts like a particle that bounces around, and sometimes it acts like a wave. So I did type this answer on the instructions of the front of this assignment in case you can't read the writing. But it says when electricity is produced by shining UV light on certain metals, which is what we talked about, using more light, remember we turned up the dimmer switch, breaks loose more electrons instead of more energetic ones. Number 4. What's the wavelength? Remember, the wavelength is lambda of the electromagnetic radiation, which is light. And by the way, radiation just means things that are sent out, including light, having a frequency. Frequency is new. They told me the frequency. What kind of electromagnetic radiation is this? So, what do we know? Well, I always know the speed of light, because that's a given. They gave me the frequency, and they asked for the wavelength. Well, that fits into this formula really nicely, doesn't it? I know the speed of light. They handed me the frequency. I'm asked for the wavelength, and I can divide and get this, because the seconds on the bottom will cancel out the seconds on the bottom when I divide this under. I'll get meters, and that is the meters. It measures the wavelength. And if you look on your EM spectrum page, I had this wrong for a moment, but I've replaced it. Find your wavelength side of the spectrum, and I think you'll agree that it's in microwaves, because the dividing line between the radio and the microwaves is pretty much 1 times 10 to the minus 1, but this is a little bit bigger than that, isn't it? So that moves it over to the left on our paper there and puts it into microwaves.